This flowchart maps the sequence mathematicians use to scale up from basic arithmetic to advanced operator theory. We start with numbers. Grouping them creates vectors. To analyze operators, we must layer on specific structural rules until we reach the final stage, the Banach algebra. The first addition turns a standard vector space into an algebra. We do this by introducing a rule for vector multiplication. For any two vectors, their product must also be a vector in the space. This multiplication follows the associative and distributive laws and includes a unique identity element labeled E, which leaves any vector unchanged upon multiplication. Next, we add norm brackets to measure distance, creating a normed algebra. The norm and the multiplication are linked by the submultiplicative property. The norm of the product xy cannot exceed the product of their individual norms. We also require the norm of the identity element to equal exactly 1. The final requirement is completeness. If a sequence of elements crowds closer and closer together, a Cauchy sequence, its limit must exist inside the space. When an algebra has a submultiplicative norm and is complete, it is a Banach algebra. Combining these specific layers creates a space where we can perform calculus-style limit operations on abstract, multiplied entities. The real number line and the complex plane serve as the simplest examples. Both systems satisfy every one of these conditions, acting as one-dimensional Banach algebras. Continuous functions on a closed interval also fit the definition. The product of two continuous functions is continuous. Since the norm is defined by the maximum value of the function, the peak of their product will never exceed the multiplied peaks of the individual functions. This submultiplicative inequality serves as the functional link between measurement and multiplication. It ensures that multiplying vectors remains a continuous operation, keeping the output size bounded by its inputs. In the space of bounded linear operators, multiplication represents the composition of actions. Applying T1 and then T2 defines the product T2, T1. This space is non-commutative. Unlike basic numbers, the order of these operations dictates the final result. We define the spectrum of these operators using pure algebra. The resultant set consists of all complex numbers lambda, where the element x minus lambda e has a valid inverse. The spectrum is the set of all values where that invertibility fails. This algebraic approach allows us to analyze the behavior of infinite-dimensional operators using the simple condition of whether an inverse exists. Theorem 7.71 provides a tool for finding these inverses. If the norm of an element x is less than 1, then e minus x is invertible. Its inverse is an infinite geometric series. We prove this using partial sums. The submultiplicative norm bounds each subsequent term by the norm of x raised to that power. Since the norm of x is less than 1, the terms shrink into a Cauchy sequence. Multiplying this series by e minus x cancels the inner terms. As the series extends to infinity, the trailing terms vanish, leaving only the identity element, e. The algebra provides the cancellation, but the completeness of the Banach algebra is what guarantees the series actually converges to a meaningful limit. Consider this problem. If x is an invertible element and y is located very close to x, how can we prove y must also be invertible? We can rearrange the expression for y by factoring out x. This expresses y as x multiplied by a term involving the identity and the distance between the two elements. If the distance between x and y is less than 1 over the norm of x inverse, then the norm of this clustered term shrinks below 1. Based on the Neumann series, any term structured as e minus an element with a norm less than 1 is invertible. Since x and the bracketed term are both invertible, their product y must be invertible as well. This creates a protective open ball of invertible elements around x. This proves the group of invertible elements is an open set. In physical systems, this property provides stability. Small perturbations won't suddenly destroy its invertibility. For an algebra that lacks an identity element, we can mathematically add one. We expand the space by one scalar dimension and define a new norm that combines the existing norm of x with the absolute value of the new scalar. These abstract structures provide the mathematical framework for quantum mechanics, where physical observables like position and momentum are modeled as non-commutative operators. Because position and momentum operators do not commute, the order in which you measure them changes the outcome. This order dependence prevents the system from existing in a state where both properties are precisely defined, a phenomenon known as Heisenberg's uncertainty principle. John von Neumann utilized these operator algebras to translate quantum observations into a rigorous mathematical language. This summary matrix tracks the buildup of these spaces. Vector spaces provide addition, algebras add multiplication, normed algebras introduce distance and the submultiplicative rule. Finally, Banach algebras ensure completeness. Mastering these rules provides the structural blueprint needed to navigate operator theory and the mathematics of the quantum world.